Alessio, thank you very much for the introduction and thank you guys for the invitation. So today, I will be speaking about some work that I've been doing with my fantastic collaborators, Mendel, who's another postdoc based in Durham, Emily, who's a PhD student of Tin, and Tin, who's a professor in Durham. So the structure of the talk, second, let me put you here. It's going to consist essentially in three parts. Okay. So first, I'm gonna have a physics introduction to a phenomenon proposed first last year by these people, in which they conjecture that there are some systems that exhibit a phenomenon that they call entropic order. Essentially, as imagine a system that exhibits that is fluid, for example, at low temperature, and then becomes ordered. So, for example, a solid at high temperature, and this spontaneous symmetry breaking persists up to infinitely large temperature. Of course, it's very tempting to jump to conclusion about technology and so on and so forth, but I will not do I will not do that in this talk. I will stick with my feet to the ground, and I will study this phenomenon in the simplest model we can think of, which is the so-called generalized Ising model. It's a lattice system with this Hamiltonian. So as you see, do you see my mouse? Uh,
Yes, you see it.
Okay, fantastic. So as you see, there is just two terms. Everything is positive in this game, in this system. So U, P, and mu are all positive parameters. Mu is the chemical potential, so it doesn't need an introduction. You already know what it stands for. And P and U instead parameterize a repulsion term that is pretty much like the Ising one, hence the name, meaning is an interaction between prime nearest neighbors in the lattice. And mnemonically, it's very easy to remember that P and U, as you increase them, you increase the repulsion, this such repulsion term. Okay, so throughout the talk, you can keep, it's very easy to remember that as you increase P and U, you're increasing the repulsion, the hate, how much the particle hate each other, essentially. And crucially, it will be crucial later, actually, this detail. I will be taking the spins per site are allowed to take any non-negative integral values. So you can think about this kind of spin as a boson occupation-like variable. So after introducing the physics around this of this system, we will pause from physics and we will enter the tour in math. So it's gonna be very light, don't worry. And I will just introduce some packing problems that are really common in graph theory and in computer science. And this then will allow us to access to the last part where we will go back to physics. And with this machinery that we will be developing during the second part, we will be able to tackle and solve the problem, essentially proving that for sufficiently large temperature, this system enters in a spontaneous symmetry broken phase. And such proof will be established for the system in the case of bipartite lattice, which is essentially what they conjectured last year. They conjectured for square lattice. We will be a little bit more general. We will prove it for any bipartite lattices. And then we'll conclude with some remarks on what could be possibly happening in case you put this system on a very general lattice or a network or and so on and so forth. So if the structure of the talk is clear, let's start with the physics intro. So this is going to be a tale about order versus temperature, and as we know, in order to settle in which phase a given system is, you need to minimize the free energy. And at low temperature, temperature low enough, minimizing the free energy correspond to minimizing the energy. Okay, this is the regime in which you all expect and love spontaneous symmetry breaking to occur. We are all familiar with this phenomenon to happen at low temperature, and I don't need to spend words about the importance of spontaneous symmetry breaking. because it essentially allows us to have phases of matter that have very, very important and interesting properties. So in this talk, I'll be focusing on lattice systems. So let's keep our life simple. Let's just consider the toy model the simplest one. So the Ising model on a squared L times L square lattice. X and Y here are the coordinate on the positional coordinates on the lattice. And so I have an Hamiltonian that is precisely this one that you know from your university's courses. And the spins are allowed to be just plus or minus one, so up or down. And we know that this system, we all know that at temperature very low, temperature that are typically lower than the typical interaction J, energy interaction scale, they are either all pointing up or they tend to pointing towards either the North Pole or the South Pole. And at high temperature, instead, minimizing the free energy correspond to maximizing the entropy, essentially. And we have all this kind of intuition coming from high school, I guess, that entropy has to kill order, because this is the regime in which thermal fluctuation, very intuitively, dominate the system. And so we have this intuition that thermal fluctuation correspond to disorder, and so spontaneous symmetry breaking or cannot occur, meaning all the symmetry have to be restored at a certain temperature. Let's look what happened in the icing. Indeed, when in this model, when temperature is much bigger than the characteristic interaction scale J, the coupling J, a typical configuration that that you might have is this one, where spins are random, essentially randomly distributed up and down, and so there is no alignment. And this doesn't seem to be something special about Ising, but actually seems to be something quite general about lattice models. Why? You can make the following statement quite rigorously. I'm going to just offer one line hand wave argument, but let's call omega the configuration space. Okay, all the configuration um, of your lattice system. Then the probability of seeing a configuration in a particular configuration is given by the Gibbs measure, as we all know. And when beta going to zero, roughly speaking, you see that when this beta is going to zero, you land on a uniform distribution on omega, on all the possible configurations. And this is precisely the concept of disorder, because like order instead would have been having a probability distribution on the configuration space that is picked around some special configuration. These were the two special configuration. So essentially, very roughly speaking, you would say that when beta going to zero, meaning taking temperature very large, you end up with disorder. But these people last year challenged this picture, and they propose this phenomenon called entropic order, and in which entropy essentially um, is able to stabilize the spontaneous symmetry broken phase. And so you can imagine like a system that is possibly disordered at low temperature and enter a phase that is ordered because of entropic reasons, and because it enters and furthermore this order phase is stable up to infinite temperature and dominant. Why is this happening? The main message is this one: because as temperature increases, the macroscopically order phase correspond to many more microscopic configurations, hence more entropy. And so in this kind of systems, and this is a very peculiar system, the system prefers to order macroscopically because in this way is able to access a lot, a lot of microscopic configurations. So if you want to cook up such a dynamics, of course, you need to avoid this one-line argument, okay, that I gave you before. So essentially, we want the Hamiltonian to survive as beta goes to zero. in the sense that as beta goes to zero, beta h cannot go to zero as well, because essentially I want some non-trivial dynamics to survive at high temperature. So again, roughly speaking, if you think about the Ising, for example, beta h is nothing but beta j and the interaction between nearest neighbors. Okay, so there are two ways. If beta is going to zero, the Hamiltonian has to go to infinity. And so this infinity has to come from either j or these ends. So to avoid this limit going to zero, either you take j to equal to infinity, but this is equivalent, this amounts to introduce a constraint on the configuration on the space of your configurations. For example, if you consider the limit j going to zero, it means that if here, if for example a site is occupied, the other site cannot be occupied. If you think about 0 and 1, for example. Let's change the variable for a second. And this is precisely something that has been already proposed and studied to death from the 80s. Okay, in such systems, the temperature essentially factorize out. Sometimes they're called athermal for this reason. Why? Because if you have J a coupling that is already infinite, which is roughly speaking what happens when you have a constraint in your dynamics, sanity to infinity is really not really meaningful anymore because there is a coupling that is already infinity. You cannot go beyond that energy scale. And what these people do last year instead is considering all coupling finite in your system, so taking j to infinite, j to be a finite value, and try to cook up a model in which as temperature is the energy scale that is much, much above any other characteristic energy scales of your system, still you have an order phase. Okay? And then, okay, so the infinite has to come from the NX. And so this is precisely what they came up with. They realized that when the spin per vertex per lattice site is allowed to take any natural number, then you might be thinking that there are some profiles of in your configuration space in which NX, for example, can grow with temperature. And so the inverse temperature will cancel out uh, this linear term in the temperature. And so beta h doesn't go to zero anymore as beta goes to zero. In other words, what Juan Komargowski, Lucas, and Popov found last year is that in one line can be summarized with the fact that interacting boson serve as an entropic path. So boson are able to store a lot of entropy. Okay? And so all the models that they build involve this idea, the fact that you can use boson to stabilize uh, entropically order phase. And without being too general, let's stick to a playground. And so let's consider the generalizing model, which is the most important example I think, in this arena in which we can see many things happening and having them under control. And so again, is this Hamiltonian, where there is a repulsion term that I explained before for Enrico who just joined. Ciao, Enrico. There is a nearest neighbors interaction, like in the Ising model, pretty much. Okay, and it's a just little mild modification of the Ising model because I'm just allowing this p, which will be fixed to be 1 in the Ising model, to be any value bigger or equal than 1. Okay, so it's just a mild modification of the usual Ising interaction. And as you increase p and u, you're increasing the repulsion of the system. And then there is a chemical potential, and here I'm forced to add because otherwise, because of these variables can take any non-negative integer, and so essentially this chemical potential must be added, otherwise the partition function is not well defined. And everything's positive, and maybe at the end of the talk I will have the time to discuss what happens for p between 0 and 1, but let's make our life simple now, and let's restrict to p bigger or equal than 1. So let's get a feeling of what's happening in this lattice system. At low temperature, well, it's not difficult to see this. At essentially, you don't have much thermal energy around, so your boson are not really excited. They don't want to come and visit you in your lab, so you rarely see them. Okay, and so for example, a typical configuration would be like having your lab completely empty, and maybe having a boson here and maybe two bosons here. Okay, and appreciate that like it's so rare to see bosons, that of course when they appear in your lab they definitely don't want to be near each other because otherwise they will pay they hate each other because otherwise you will need to pay the penalty energy um, from their portion term. You're already paying energy, the mu for each boson, you're paying a mu penalty energy to have them visit your lab. Clearly, you don't want to pay additionally on top of that also a U penalty, energy penalty. So they're far apart. And throughout the talk, it's going to be quite useful actually to introduce this pictorial way of understanding this system. So I'm going to color a vertex in blue if there are some bosons. Could be one, could be two, could be 7,000. Okay. And white if there is no boson. If your lab, that vertex is still empty, there's no bosons there. So, a typical configuration in this pictorial way would appear like this, white everywhere, empty space. But sometimes you see some vertices switching on. Kind of like, when you're in front of the sea, um, and in a tropical country and you check for bioluminescence effects, you see sometimes the ocean switching on. Um, okay, so this is what happening at a low temperature and what happens at high temperature. Well, now your bosons are quite excited. They're thermally excited, they have a lot of energy, and so they don't care. You don't care anymore about the fact that you need to pay a U or mu penalty because you have so much energy in the system that you're rich, you're afford to pay this price. So essentially, bosons start visiting your lab quite easily. And there are so much of them that, now you need to come up with a strategy. You need to tell me how do I accommodate all these bosons that come to visit your lab. And of course, at high temperature, we need to maximize the entropy. And so, the first maybe too naive solution for this problem would be, okay, let me quite be quite democratic and let me put the bosons a little bit everywhere. Why I will think that? Because I will naively think that if all sites fluctuates, if all sites are allowed to host bosons, then every site, in every site I will host fluctuations, and so I will be able to access a lot of configurations, microscopic configuration this way. This might be too naive because if I put boson everywhere, the U term is going to be active. Okay, and so this boson, the typical fluctuations, is going to be severely capped, okay, by this Euro Poisson term. And so, in order to avoid this mechanism, this capping mechanism, you could think about an alternative. So I could accommodate my bosons only in a checkerboard pattern, meaning in half of the lattice, okay, and so I will have like this kind of um, checkerboard checkerboard pattern. And in this way, you see that every blue share an edge only with y's, okay? Meaning that this U proportion term is essentially killed, is not active. And so, like even if only half of the size fluctuates, and so naively you think that this corresponds to less entropy, because these fewer terms are uncapped, okay, by the U term, they're allowed to fluctuate much widely, more exuberantly, okay? And so it's not clear which is the entropic winner. You need to do a computation. Before settling this computation, let's just me stress that, if you distribute bosons quite democratically, you are in the disorder phase, okay? that you can think of as a gas phase, because as usual, translation invariance, we call it gas because the translation invariance, by analogy to what happens in the continuous case here, translation invariance, the one which here discretized because you're in the lattice, is preserved. We call instead this ordered phase, where there is a pattern to be preserved, this ordered phase a solid phase, in analogy with the continuous case, because here the translation of the lattice is spontaneously broken. So we need to settle this entropic competition, okay, between the solid and the gas. The first order approximation we can do, as usual, statistical mechanics, to do computation is mean field theory analysis, which essentially tells you that, like this typical fluctuation number, okay, in the gas phase, goes like t divided by t by 2u to this power of p. And indeed, you see that this typical fluctuation um, per site in the gas phase is capped by u and p. As you increase p and u become smaller. It's precisely as you would expect. And you see that because p is bigger or equal than 1, you see that anyhow it cannot grow faster than square root of t. So, the gas phase are capped to square root of t. Okay? So let's compute the entropy, very roughly speaking. We have the log of all the configuration that the system can access in this phase. Well, how many configuration? Roughly speaking, if every site can fluctuate up to this characteristic fluctuation scale, well, then I'm going to have such scale for L square lattice, because I have L square lattice, all of them are switched on. And so the entropy for the gas, roughly speaking, is this one. Let's do the same mechanism for, let's say, same analysis for the solid. Here it's so easy. You don't even need mean field theory, because again, the repulsion term is not active, so there's not interactions. And just by looking at the Hamiltonian, you see that if the blue terms, while the white terms are fixed to 0, the blue terms are going to be capped just by u and beta, meaning they're allowed to go like t divided by mu, like a free theory, okay, of bosons. And so the entropy of the solid is going to be the logarithm of the number of blue sides. I have L squared divided by 2, because only half of the lattice is colored blue. And to the typical n bar is this scale this time. So, just by checking these two entropies, okay, in these two papers, respectively, I think published in March and in August last year, this gentleman proposed that for p bigger than 1, you see the solid always win. The solid win parametrically in team. See, so it wins like super a lot, okay, like by far, okay. For p equal 1, and this is interesting, and you see that the entropies of the two phases have the same power of t. And so, like, this entropic competition is going to be settled by not by the exact value of u and mu. And just by comparing these two numbers, they propose, and this was confirmed by Monte Carlo simulation actually, that for u bigger or equal than mu half, at high temperature you have in a solid phase, and for u smaller than mu half, instead at high temperature you have a gas. And so there's going to be, at high temperature, you're going to have a transition between gas and solid, depending on the value of mu and u, which is extremely interesting. So let me just mention Monte Carlo. Here, let me steal some picture from their papers. Monte Carlo literally confirms the intuition coming from in-field theory. Okay, so for p bigger than 1, for example, at low temperature, you see a gas, a democratic region. And at high temperature, instead, you see a checker pattern, which is quite striking visually, emerging. And but Monte Carlo cannot be, of course, a proof of anything. It just confirms that you're in the right way of thinking, and that the physics that I described to you in the previous slides seems to be the correct one, but you are not sure. Of course, it's very unlikely that this might happen, but you cannot be sure that you cannot make a Monte Carlo simulation at infinite temperature. You cannot simply do it. On top of that, this is a regime, this model is a regime. If you look closely, you will discover that you're applying mean field theory precisely in a setting in which you shouldn't be applying. In other words, mean field theory in this model seems to be plagued with huge fluctuation, and so you don't understand why in principle, you should be the result from mean field theory are reliable or not. And this is the reason why we start thinking about, okay, but and the physics of the system is clear. Monte Carlo seems to confirm this. Mean field theory seems to confirm this. Can we actually prove it rigorously? And this is the what I'm going to present to you at the end of this talk, essentially. But this is a very good moment to ask for a question, I guess, if there is any. If the physics is clear, let's take a detour in the math literature. It's going to be very easy, don't worry. And so now let's consider a general graph, a network. So no symmetries, okay? So no spontaneous symmetry breaking, no symmetries, nothing, not even temperature, nothing physical. Just I give you just a graph, as simple as that. Let's take a detour, and I give you a graph, and and ask you on a general graph, on a general lattice, which pattern is gonna replace the checkerboard pattern? Why is this question relevant? Because remember that at the end of the day, we want to prove that the checkerboard pattern or a generalization of it is the pattern that will emerge at high temperature. So we need to understand what 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 is making the checkerboard pattern so important, okay, from mathematical point of view. So I already gave you before two rules. There you go here to build a checkerboard pattern. So let's try to generalize to to general lattices. The first rule was telling you, okay, on two occupied sides, two blues, cannot share an edge. Otherwise, you will be severely capped by the Euro portion. So it means that the generalization of the checkerboard pattern must consist of isolated vertices. So for example, if I, out of this network, I take this vertex and I cannot pick also these two, and so on and so forth. And so, for example, here, this is a pattern that is a possible generalization of the checkerboard pattern that consists of only three isolated vertices. This is precisely what mathematicians call independent set. So given a graph, an independent set of that graph is a subgraph that consists of only isolated vertices. But there is also a second rule because the checkerboard pattern cannot be any independent set because we also want to maximize the size of the independent set so as to remember we don't want only to have isolated vertices. We also want to accommodate the highest amount of isolated vertices in my network because every vertex at the end will fluctuate. And so every vertex carries some entropy, contributes with some entropy, and you want to maximize the total entropy. And so, for example, in this network, you see that the maximum independent set, meaning the independent set with maximum size, consists of four isolated vertices. And there you go. So we found the concept that generalized the checkerboard pattern, the so-called maximum independent set, or MIS for short. In a very easy network like this one, I just told you that find the highest amount of isolated vertices. All of you could find that very quickly. And like I could find that as well by eye. It's this one, this four. But imagine having a very general and complicated graph. You just want to put this concept of maximum independent set on the computer so that you press Shift Enter and there you go. It gets isolated for you. So how do we put this on a computer? Well, To each vertex, you associate either 0 or 1, white or blue. Okay? And then for each edge, you impose that their sum cannot be bigger or equal than 1, because I cannot have blue near a blue, meaning I cannot have 1 plus 1. I can have 1 plus 0, 0 plus 1, or 0 plus 0. And then, out of all these possible configurations, you know, I want to maximize the number of blues. I want to maximize the number of ones. So I want to maximize this linear function. When meaning I want to maximize the number of isolated vertices. Okay? And the solution to this packing problem, because you see that you have some constraint, it's like having a volume, it's like having a backpack, okay? And you want to maximize the number of oranges that you put inside of this backpack, subject to a constraint that these oranges don't like each other too much, so they need to have a little bit of room. They cannot be too close to each other, essentially. This packing problem, the solution to this packing problem is called the size of the maximum independent set. And of course, there are many, discretely so, many different maximum independent set that a graph might have. And funnily enough, this problem, which is the easiest packing problem, the most natural packing problem that you might be thinking as soon as you have a graph, in general, is non-polynomial hard. So what happens? Every time you have a non-polynomial hard problem, well, what do you do? First of all, you cry. And second, you map to a problem that you can approximately solve, that you can solve, and then can give you an estimate of the alpha that you were looking for. So what you do, you associate this integer problem. As usual, you know that integer valued problems are nasty. And so you relax this integer constraint, these variables that lives on each vertex, not only to be either 0 or 1, but actually you relax it to take any possible values between 0 and 1. Okay. And then you have the same edge constraint of before. And then you maximize the same objective function of before. Of course, now you're searching for the maximum in a bigger set of before. So this alpha f, which is the size of the maximum fractional independent set, is going to give you an upper estimate, an upper bound on the alpha that you were not able to compute before. And because here everything is convex and you can play a lot of tricks, actually, you can compute this alpha f in a polynomial time. Okay? So this alpha f, when you see in this talk f subscript, it means fractional. It means that I'm allowed to have half person per site. Okay? And this fractional independent set size give you an upper estimate on the alpha that you were not able to compute before in reasonable time. Because now you're in the continuous case, a continuous moduli space MF of different maximum fractional independent sets may exist. So let's see some examples.
Enrico, can I ask you a question?
Yeah, whenever, guys.
Like, first of all, if you could give me maybe an intuition for why replacing discrete values with continuous values changes the nature of the problem so drastically. So it goes from non-polynomial to hard to polynomially hard. Like if you have also a bound on alpha f, because since it is bigger than alpha g, then in principle it could be extremely different, no, than alpha g, which is the object you're interested in.
Yeah. First of all, like something that is, you see that this is, let's start from the last question. So alpha G grows, is clear by the definition of these two entities, okay, these two objects, they both grow linearly, extensively in the size of the graph. So, if you take the ratio, the extensities cancel out, and so you're left with order one number.
Yeah. Okay.
So, alpha f cannot be like 2700 and alpha g1.
Yeah, right.
They're,
Okay.
they're, the so-called integrality cap, meaning the ratio between alpha f and alpha, if you want to Google, it's called integrability cap. is small usually. I mean, typically order one number. I mean,
Okay, okay.
uh, yeah. So first this, and second, I don't remember the first question. And the intuition. Yeah. So well, even solving just a solution, like take a you say that you're searching the zero of an equation. If this equation is integer value, you know very well that even Mathematica Stagos takes a lot of time,
Okay.
right? Press Shift Enter. This is a typical thing because for integer values, roughly speaking, this is my intuition. This is not a theorem, but roughly speaking, you need to check. Uh,
Okay.
you need to check a lot of cases essentially. And but essentially when you instead are in the continuous case, you can take gradients, you can take Hessians, like, and in this case, you see everything is convex. So, and everything is linear, it's convex. So you're in the best case scenario possible ever. Like,
Okay, okay. I got the idea. I got the idea. Thanks.
eh, welcome. And yeah, so just some examples. You see, for example, in this case, alpha and alpha f are the same, give the same. And is actually this property of all bipartite graphs. So when you have a bipartiteness, alpha and alpha f are exactly identical. And so you can compute, by computing alpha f, you can exactly compute alpha in polynomial time. Okay? But when you have a non-bipartiteness, so for example, triangular lattice, you see that take a triangle, how many maximum independent set do I have? Just three, because like each one of them consists of just one isolated vertices. You cannot accommodate more than one isolated vertex in a triangle. Okay, it's the usual story of the frustration in the Ising model is the same thing. So, but what happens if you relax to fractional occupation number? Well, there I can put half of a person here, half of a person here, and half of a person here, and so I get 3 half. You see that is bigger. Okay, but the ratio is order one. Okay. So here you see that the solution is unique, so there is no moduli space, okay? But instead, in this case, okay, in the open chain with 4 vertices, for example, there is a continuous, moduli space of dimension 2. Here I put like all the solution of your maximum fraction independent set. And if you take the sum of these guys, what you get 2, okay? And okay, so this is the end of the second part of the Mazzi the tour. So, are there any questions? If there are no questions, we can go to the third and last part of the proof, part of the talk, in which I'm gonna sketch in 4 slides how we prove entropic order for this model, because now we have all the machinery at hand. So, first of all, the idea was let's use the so-called activation variables, which is the blue and white variables that I introduced for you before. And so I'm gonna switch coordinates and I'm gonna go to the coordinate x, which is 1 when there is something in that vertex, and 0 when there is nothing in that vertex. Okay? Then, in these, if you describe the system in terms of these very coarse-grained variables, okay, what you're gonna get, of course, is that the partition function is gonna factorize in very many sectors. And now what you want to check is that is the miss sector, the maximum dependent set sector, the pattern that emerges when you send t out to infinity. You want to check that out of all these possible sectors, the miss sector is the one that dominates, is the dominant one as t grows large. So let's pick up any of these sectors. We need to compute how it scales with temperature. Okay. So because any sector consists of white and blue vertices, okay, occupied and unoccupied, just because in the white vertices there is nothing, I can just forget about them and just sum over the blue ones. Remember that the blues one the white one, and it's fixed to be 0. So I can just forget about it. And there's literally nothing there, okay? So it cannot contribute to the weight. The blues ones, I'm summing from 1 to infinity, okay? Because there is something there. And so, if I forget the whites, like I'm left just with the so-called induced subgraph. From now onwards, I will call it G. G will be the induced subgraph of a sector. How do I get the induced subgraph? Again, you forget about the whites, you just neglect them, and you connect by using the edges the blue dots. Okay? And the weight of this in the subgraph, of course, it will factorize into the weight of its connected components. Why? Because, the only thing I did was to forget the whites. And in the whites, there is literally nothing. Because there is physically nothing on the whites, it means that these white dots couldn't possibly propagate effectively any interaction between the connected components. Okay? And so the weight of any sector factorizes into the weights of each single connected component. And of course, here it's going to be super important to make a distinction because remember that we are hunting for isolated vertices. We need to make a distinction between isolated vertices, like for example, these two, from these animal-like shaped connected components. So, in general, any weight is going to decompose in this way. Okay. The weight associated to the induced graph G is going to have the weight of an isolated vertex to the power of, how many isolated vertices I have. And then there is going to be the product over the weight of the other animal-like configurations, meaning configuration that are connected and consist at least of two vertices, like these things. Okay, so let's see how any of these fundamental building blocks of your theory scale as t goes to infinity. So the weight of a single isolated vertex, again, is the same computation that I proposed to you like some slides ago. In this case, like there is no U term, so it's just the chemical potential, T divided by mu. And then the weight instead of a connecting component, this is much more non-trivial. And let me just state for you the result. I have backup slides in which I can show you this. It's quite instructive, quite interesting to see this proof actually. And in the paper, we propose a pure analytical way, which is very safe, but I have some slides in which I can propose this in a very geometric and very clear derivation of the result. But let me just state to you that when you compute these connected component weights, the weights of this connected component, you find T divided by U, because of course there is the repulsion term that is active, to the fractional maximum independent set size of that animal shaped component. And then there is also a logarithm that scales locally with the dimension of the maximum of the moduli space associated to this packing problem, to the fractional packing problem. Okay, let's forget about the logs because for the fewer things that I want to share with you today, they're not going to play a relevant role. So if you just keep track of the power of t's, if you plug everything back into here, this is the composition, you'll see that you're going to have t to the power of a number of isolated vertices and t to the sum over all the alpha f of your animals. Okay, these sums over animals is very cumbersome, so let me use the additivity of alpha f, okay, to get rid of this sum, to hide this cumbersome sum, okay. Of course, the alpha f of the induced subgraph is gonna be the n iso because I've the alpha f of just one isolated vertex is 1 plus the alpha f of all the animal-like shape. And so I end up with this exponent. And so we're done because I had given a sector. I computed for you how it scales with temperature. And you see, it's a little bit tricky because, like we need to show that this exponent is maximized for the miss. So let's conclude. The sector that dominates at high temperature is the sector that is identified by induced subgraph G that maximize this exponent. On a bipartite lattices, on a lattice, you have this further simplification that I explained to you before. And so under this assumption, it's very, very easy. It's one line proof to prove that for P bigger than one, the dominant G, the dominant configuration, the dominant G is precisely the miss of the lattice. So for example, on a two-dimensional square lattice is the two checkerboard pattern. And so we are done. I say that it's just one line, but without going to the details, the reason why this is very easy to see very intuitively. You see that for P bigger than 1, this term survives. If alpha f is equal to alpha g, you have alpha here, and alpha, remember, is the maximum number of isolated vertices. So essentially you have n iso plus n iso. And so if you want to maximize this exponent, essentially you want to maximize an iso. But by definition, the miss is the pattern that maximizes the number that accommodates the highest amount of isolated vertices. So it's very trivial. For p equal 1, so this term gets erased, and so it's much, much more subtle to understand which ones are the components that actually the sector that dominates. And essentially, we found that all the configuration that dominates at high T corresponds to a checkerboard pattern, and then a checkerboard pattern plus bubble of gas on top of it. I can share more details later, but now essentially the further complication that you have in this marginal case is that you need to keep track, you need to take under control this bubble of gas. You need to make sure that don't proliferate, that their size is small. Okay, and we can do this by means of a bias argument, something standard in the statistical mechanics literature. We can prove that essentially this bubble of gas don't proliferate when this ratio is big enough. Whether big enough means bigger than 1/2, as forecast and conjectured by the mean field theory analysis and Monte Carlo, this is still an open question. And further direction, and so okay. So let's conclude. And we saw that the sector that dominates at high temperature is the sector that is identified with the subgraph, induced subgraph G that maximizes this exponent. We saw that in the case of the bipartite lattices, we could settle entropic order. What happens now if we put this model instead on a general graph? Okay. So remember and that we still have to maximize this exponent. Okay. And but now this time there is an integrality gap between alpha f and n iso. So essentially these two terms compete with each other. Okay. So to disentangle this competition between these two terms, because it's not clear what you need to maximize, okay, let's send p to infinity. What happens if we crack up the repulsion term? Well, you see clearly that when p goes to infinity, this term disappear, and you're left with n iso. So if you want to maximize this exponent for p large enough, again, you must land on what? On the miss. So the dominant G, again, are going to be the miss of the lattice, but I told you before that on a general graph, when there is no bipartiteness involved anymore, computing these, isolating such a miss, computing alpha, is a non-polynomial hard problem. And so you will expect that in this case, the system will have very strong difficulties in thermalizing, and essentially will take forever to thermalize. And so we have this intuition that this should be the case that should correspond not to a solid at high temperature, but to a glass. And we baptize this phenomenon entropic glass. And this opened the windows to a lot of interesting phenomenology, because now the kind of phase diagram that you might have at high temperature as P varies, it could be very, very interesting. And so this is an open question. This is what we are investigating at the minute. Let me conclude a bit just with these these uh, these um, this picture. If you compute if I give you like the partition function, you can take the log of it, take the derivative with respect to temperature, and find, like the energy of the system. Okay? And so essentially, you can compute the equipartition theorem that you know that from high school, that in the gas in the gas that you know from high school, if I n degrees of freedom, the equipartition theorem scales like n. Okay, because at high temperature, every vertex essentially is free to thermally fluctuate as they want. Okay, so if I have n degrees of freedom, the equipartition theorem is going to go like n, scales like n. And this is precisely what you find for p smaller than 1/2 in this system. So, you know, I didn't show this in detail, but like this uh, this derivation, okay, this derivation actually assumes p bigger or equal than 1, as I stated at a certain point previously. Okay, so actually, this exponent that we need to maximize works only for p bigger than 1. Okay, for p between 0 and 1, you need to redo the analysis. Okay, and this is the result. Okay, and instead for p bigger than 1, you can use the analysis that I gave you before in the slides, and you see indeed that for p small enough, p almost 1, this term essentially is killed. And so you're going to have that the equipartition theorem captured only the first term. And then for p big enough, meaning p essentially above the integrability gap, okay, you're going to capture the n iso, as I explained here. So, with what I explained in the slides of today, this exponent applies here, and it tells you that the equipartition theorem is captured by alpha f or alpha. If you redo the analysis, instead you're going to find the size of G and this combination. So it's an interpolation between the size of G, which is precisely the typical gas that you would expect from your high school, and this maximum fractional independence set size, set gas-like. So you see, these are very interesting phenomena, because what is this generalized equipartition theorem is telling us is that for when the repulsion is not big enough, smaller than 1/2, essentially at high temperature, you have this kind of gas, which is the typical gas, very similar to the gas that you have from high school. You can cap a little bit the P parameter, and you start seeing alpha F appearing. Alpha F essentially tells you that some correlation survives at high temperature. Okay? You increase it even a little bit more, and you can completely forget about your high school gas. It's alpha F now that gives you the counts the degrees of freedom of this system. So now alpha F that until this line was just a mathematical idea, mathematical concepts, becomes incarnated in quite a physically clear quantity, because alpha F in the system computes the thermally the thermal degrees of freedom of your system at high temperature. And if you increase even again the repulsion to such a point that they hate each other so much that they cannot stand them anymore, and so they want to really repel a lot, it's not going to be alpha F, but alpha to count the quantity that capture the degrees of freedom that are thermally excited in your system. And so we see that alpha and alpha G, alpha and alpha F becomes very physical quantity. And my time, I think, is up. And this was my last slide. But let me just conclude by saying that, like for me, when we found these things, for me, it was very beautiful, because something that, again, you enter in a library, and you go to the maths department and you start studying about alpha F, alpha, the moduli space, and this and that, and then bang, they become like something physical quantity, like something that maybe even in the lab, maybe you can compute and check. And this system that seems strongly interacting, meaning like because the fluctuations are wild, the thermal fluctuations are wild as T grows, it's mapped to a packing problem at high temperature. Just a packing problem. There is a reason why. I have some backup slides, so if people are more interested, I can show how to prove this actually. But this is a good point where to stop in a self-consistent way.